This lecture is about type reconstruction in System F. Type reconstruction in System F. Let's first review System F that we learned in the last lecture. So this is the syntax. So we have syntax. First, types. We have this function type, and for expressions, we have this variable and lambda abstraction and application. And for values, we have this lambda abstraction. So for the system, the language looks like a simply typed lambda calculus because we have this lambda abstraction with this type annotation and lambda application and so on. Now, new to System F is type variable alpha and polymorphic type, this for all alpha A. And in the expression, we have two new components, which is type abstraction, capital lambda alpha E, which introduces new type variable, and type application, expression E, applied to type A. And this type abstraction is also counted as a value. So this is the syntax for System F. So in comparison with a simply typed lambda calculus, we have this type variable and polymorphic type, and this type abstraction, and this type application. Now, what about the reduction rules? For reduction, let's reuse the reduction rules from simply typed lambda calculus for this lambda abstraction and lambda application. Then we need new reduction rules to deal with this one, this type application. There's no reduction rule for this type abstraction because this is a type, this is a value. So we have two reduction rules for this type application. The first is expression E is not a value, so expression E reduced it to another expression E prime, and this one reduced it to expression E prime applied to type A. And if everything goes okay, then this expression E would produce a type abstraction. So capital lambda alpha expression E applied to type, concrete type A. At which point, we perform something like a beta reduction. So we substitute this type, concrete type A, for this type variable alpha. So now we have A for alpha in expression E. So notice that this substitution, A for alpha, is applied to every part of this expression E. This is another type, this is the expression. And this makes sense because inside the expression E, we may have type variables. So for example, this is an expression, and inside this expression, we have a type A, and this type A might contain type variable alpha. And similarly here as well. So these are the two reduction rules new in System F. And what about the type system? So for a type system, we have to first extend the definition of a typing context. The typing context, the gamma, is either empty or we have this type binding. And in addition, we have this type variable declaration, alpha type. So this one declares that alpha is valid type variable. Now, remember that this typing context gamma is actually ordered. The order of a component in typing context gamma actually doesn't matter. And for judgment, we have two kinds of judgment. The first is type judgment, gamma turnstile A type, and the second is the ordinary typing judgment, which says under typing context gamma, expression E has a type A, and this type judgment says under typing context gamma, this A is a valid type, which implies that not every type is valid. So for instance, if you have an alpha arrow beta type, this type makes sense only in the presence of these two type variable declarations. In order to use this type variable alpha and beta, you have to first declare these two type variables somewhere in the typing context. So in order to filter out those types that are invalid, we introduce this type judgment, this typing judgment. Now let's look at the inference rules for first this type judgment. So we have only three forms of types, so perhaps we will have three inference rules for this type judgment. So the first is, when can we deduce A arrow B is type, valid type? Well, we have to check that A is valid type and also B is valid type. And next, when can we deduce type variable alpha is valid? Well, you have to first declare this type variable alpha, so which means that alpha type should be found in typing context gamma. If this is not found in gamma, then you are not permitted to use type variable alpha. And finally, what about this polymorphic type for alpha A type? So you have to make sure that A is a valid type, but inside the type A, you might have several instances of type variable alpha. So you assume that alpha is a valid type. And then if A is shown to be valid, then you deduce that the whole type, the polymorphic type, is also valid. These are the three inference rules for this type judgment. And what about the typing rules for this typing judgment? For this lambda abstraction and lambda application, the typing rules are precisely the same. So let me just quickly write these two typing rules. So lambda x a dot e has a type A arrow B if expression E has a type B. This is arrow introduction rule. And the application is, if expression E has a type A arrow B and expression E prime has a type A, then the whole expression has a type B. This is arrow elimination rule. And what about this type abstraction? Because this type abstraction, perhaps it's going to have type, this polymorphic type, for all alpha something. Now we have to figure out this type. So in order to figure out the type, you have to find out the type of this expression E. So you check that expression E has type A. But inside the expression E, you are permitted to use this type variable alpha. So you assume that alpha is valid type. If expression E is shown to have type A, then we deduce that the whole type abstraction has a type for all alpha.A. And if you read this rule top down, you end up introducing this for all. So this is the for all introduction rule. And for type application, we have expression E applied to type A. In this case, expression E is supposed to have this polymorphic type. So you have for all alpha.b. And now we are going to substitute this type A for this type variable alpha. So it's time to check its validity. So we are going to test if A is valid type. So only when A is valid type, we can apply this type abstraction. So it has type A for alpha in type B. So this rule is called for all elimination rule, because if you read this rule top down, this for all is eliminated. So this is the type system. Now we'd like to state the type safety. So again, just like a simply typed lambda calculus, type safety, it consists of two properties, progress and type preservation. In fact, these two theorems, progress and type preservation, their statements are precisely the same as in simply typed lambda calculus. So let me write them again. So progress says if we have a closed well-typed expression A, then either expression E reduced to either expression E is a value or expression E reduced to another expression E prime. So that's the progress. And type preservation. So if we have this well-typed expression E, and suppose that we know that expression E reduced to E prime, then this type preservation guarantees that expression E prime has the same type A. So their statements of progress and type preservation properties are precisely the same as in simply typed lambda calculus. So we are not going to give all the details of the proof, but I'd like to give the gist of these proofs, which actually consists in the formulation of three substitution lemmas. So remember that in the proof of type safety, this type substitution lemma, substitution lemma played a key role. But the situation in system F is slightly more complicated because we have not just one substitution lemma, but we have actually three different substitution lemmas. Because we have, first of all, we have two kinds of variables. First, we have expression variable x, and we have type variable alpha. So perhaps we will need a substitution lemma for this variable x, and we also need another substitution lemma for this type variable alpha. And it turns out that for this type variable alpha, we actually needed two substitution lemmas, because alpha can appear inside in expression, actually type. So that's the first case. So type variable alpha may appear in type A. So in order to deal with this case, we needed the first substitution lemma for this type variable alpha. And the second case is this type variable alpha may appear in expression E. So for instance, we might have lambda x a dot E. So this is an expression, and this expression contains this type, and this type might have type variable alpha. Or we have this type application. So this is an expression, but this is the type. So inside the type A, you might have type variable alpha. So it makes sense to try to apply substitution for this type variable alpha, not only in types, but also in expressions. So it turns out that we need two forms of substitution lemmas for type variables, and another substitution lemma for this expression variable. So let's state all these three substitution lemmas in system F. So the first is, let's start with the substitution lemma for these expression variables, because we have already seen a similar substitution lemma when we learned simply typed lambda calculus. So the first substitution lemma is stated like, suppose that we have expression E of type A, and in the case of simply typed lambda calculus, the substitution lemma is stated like gamma x A expression E prime has type B. Let me erase this one. Then we have gamma E for x in expression E prime has a type B. So we want to extend this statement. We cannot actually reuse this statement because, unlike in simply typed lambda calculus, gamma is now ordered. So that's a big difference. So what that means is that this type binding is not necessarily found at the end of this typing context. So we have to generalize it. We have generalized the form of typing context here, because this type binding is not necessarily found at the end. That implies that we have to make an assumption, more general assumption. So this type binding is followed by another typing context gamma prime, and now we have expression E with a expression E prime with a type B. So that's the assumption. All this because this typing context is now ordered. Then how do we fix this conclusion? Now we are going to substitute expression E for variable x. So therefore, this will be gone. This type binding will be gone. Then we are left with gamma and gamma prime. And now we are going to substitute E for variable x in expression E prime. And it's going to have a type B. And notice that this type A is valid under typing context gamma. So therefore, this type A also makes sense. It's valid because it is given precisely the same typing context gamma to the left. So that's the first one. Now let's talk about the substitution lemmas for this type variable. So first, let's assume that A is valid type. Now, let's suppose that in addition to the existing typing context gamma, now we have this type variable alpha. And remember that this alpha may appear in a type like B, and also in expression in E. So let's first deal with the first case. But just like this example, this type variable declaration is not necessarily the last element in the typing context. In other words, it may be followed by another typing context here. So we assume that we generalize the statement and we have a gamma prime here. And suppose that under this typing context, we have another valid type B. Because V is valid type under this typing context, this alpha may appear inside the type B. So if we apply type substitution on type variable alpha, this type B is also subject to this type substitution. So then what is the conclusion? So if this is the case, then we are going to substitute A for alpha. So this guy will disappear. So now we have a gamma and gamma prime. And then inside the type B, we might have a type A, type variable alpha. So we are going to replace this alpha with this type A. So this is also valid phi. But it turns out that this is not the end of the story, because yes, of course, this alpha might appear in type B, but the same type variable alpha might appear inside the typing context gamma prime as well, but not in gamma, because this gamma is found to the left of this type variable declaration. So for instance, inside this typing context gamma, we might have a type binding, something like y colon alpha arrow alpha. So in which case, this alpha should also disappear. Otherwise, after applying this type substitution, this alpha is not accounted for by any type variable declaration. So this implies that the same type substitution must be applied not only to this type B, but to every component of this typing context gamma. So for instance, if gamma prime has this type binding should be rewritten as y colon a arrow a. So for that reason, so it's not enough to apply this type substitution only to type B. You have to actually apply this type substitution alpha for A for alpha to every component of this typing context gamma. So here we slightly abuse the notation. So what this thing means is that you apply this type substitution to every type binding in gamma prime. So this is the right way of formulating the second substitution lemma. And finally, we have the last substitution lemma that is similar to the second one, but deals with expressions. So you have this type, valid type, and this time you have typing judgment. This is type judgment, but now we are going to have this typing judgment. This is a typing judgment. Then what happens? So we are going to substitute A for alpha. So this one will disappear. And just like the second case, this typing context gamma prime might have lots of type variables alpha in it. So you have to apply this type substitution to every component of typing context gamma prime. And then what happens? Expression E has a type. Well, this type B might contain the type variable alpha, so you want to apply this substitution, type substitution to type B. But actually, that's not the end of the story, because this expression E is also subject to this type substitution. So for instance, this expression E might have something like lambda x alpha dot x. In this case, this type variable alpha, which is found inside the expression E, must be also replaced with this type A. So because this expression E may contain this type variable alpha, you have to actually apply the type substitution to this expression E as well. So you have to apply this type substitution to this expression. So this is the last form of substitution lemma in system F. So all these three substitution lemmas look quite complicated and may even appear almost unnecessary, but if you think about the relation between types and expressions, in particular type variables and expressions in system F, you will realize that all these three substitution lemmas are necessary. And these statements look a bit more complicated than in simply typed lambda calculus, but that's what we have to. That's because its typing context gamma is now ordered. This concludes the discussion of type safety, starting with the syntax, reduction rules, and type system of system F, and we have formulated type safety, progress, and type preservation with these three substitution lemmas. So I guess the key in the proof of this type safety actually lies in substitution lemmas. Substitution lemma is actually the gist of the whole proof. Now let's talk about type reconstruction. So let's think about this lambda abstraction to see why we need a type reconstruction. So in this lambda abstraction, we make an explicit annotation for the type of this variable x. We explicitly write the type A that should be assigned to this variable x. The question is this type annotation? Is this type annotation absolutely necessary, or is it preferable? Is it necessary? Is this necessary? So you might claim that writing this type annotation is always a good idea because it gives you more information about this expression. In practice, it may not be actually a good idea to write this type annotation every time. Why is it that? So the claim is not necessarily. It's not necessarily a good idea to write this type annotation. And the first reason is it actually hurts code readability in some cases. Code readability is bad. So here's an example. Let's compare two functions, let's say written in OCaml or in a similar language or hypothetical language. You have function x, function y, and x plus y. So in this example, there is no type annotation. And let's contrast it with another equivalent expression with type annotation. So these two expressions are completely equivalent because their behavior, runtime behavior, is exactly the same. And the question now is, which is better for code readability? So people might have different views and opinions about which of these two expressions provides higher code readability, but somebody could claim that actually this is bad, this is actually better, because even though in this example we don't write the type annotation, The reason is, when we look at the expression, we can instantly tell the type of these two variables thanks to this plus operation. So in the presence of this plus, this addition operation, we can tell that these two variables must be of type int. So even though this type annotation is not provided, we can instantly tell that these two variables must have type int. So in this second example, we give explicit annotations, type annotations here. But actually, these type annotations are, in practice, these type annotations are unnecessary, and they are even detrimental to code readability, because in practice, they are unnecessary. So we could claim that it's fine in many cases not to provide the type annotations like this. We are still fine, as demonstrated by this example. So in the same line of thought, what about comments in your code? It turns out that writing a lot of comments is not actually good practice. Perhaps you are encouraged or even instructed to write the comments in every part of your code, but writing a lot of comments, writing verbose comments is actually bad practice. So whoever gives the advice of writing, having to write the comments in every part of your code, perhaps has no serious experience of writing programs. So we can talk about this topic in class, in the online meeting, if a student want, but the situations are quite similar. Writing a lot of comments is not necessarily a good idea. You want to be frugal in writing comments, because comments are often detrimental to code readability. In particular, if you can make a good use of types. Types are perhaps the best way of writing documentation. So back to the discussion of type annotation. The question is this type annotation necessary? And the answer is not always, not necessarily, because it's better for code readability. And more importantly, type annotations are unnecessary because if you design your programming language carefully, you can actually reconstruct the types, or you can infer the types. In this example here, if you design the programming language carefully, it's a type system, then the type, perhaps you can implement a type reconstruction algorithm, which infers the type for these variables. The type reconstruction algorithm will tell you the variable x must have a type int, because it is an operand of this integer addition. So depending on the way that you design and implement the programming language, you might be able to reconstruct the types. In that case, this type annotation is actually not always necessary. So this is the point where we broach the topic of type reconstruction. So we start with a language, for example, with a no type annotation. Here, no type annotation. And we'd like to automatically annotate this expression E with the type annotation. So we produce expression E prime. And this is called type reconstruction. So basically, we reconstruct the types, or we infer the type for every part of this expression E. So in the case of system F, so this is the system F, which is definitely typed language. And the source language is actually untyped lambda calculus. So that is, we take an expression in untyped lambda calculus, and then we add the type annotations. So for example, we annotate this variable with its type in lambda, and we also introduce type variable, and we also introduce this type abstraction. And then we produce a corresponding expression in system F. And that's how type reconstruction works. But of course, this expression E prime must be connected to the original expression E in some way. You cannot just return a random expression in system F given this expression E. So these two expressions must be connected in a strong, in some way. And to formalize the connection, we could introduce an eraser function. So this eraser function takes an expression in system F. This is system F. Let's say this E prime. And it returns an expression E in untitled lambda calculus. And the idea is that we just erase every part of this expression E prime that is related to types. For example, this type annotation will be discarded. This type variable will be discarded, and this type abstraction will be discarded. Then you get back an expression in untyped lambda calculus. So the requirement in this type reconstruction is you start with an expression in untyped lambda calculus, and you run this type reconstruction algorithm to produce a corresponding expression in system F, say this E prime. Then you should be able to show that expression E prime satisfies this equation. If you erase all these type related stuff, then you get back the original expression E. So that's how we formulated the problem of a type reconstruction in system F with respect to untyped lambda calculus. And it's pretty easy to define this eraser function. So let's write the definition. So if you erase a variable x, there's nothing to erase. If you erase this lambda abstraction, so this is a system F, so you have this type annotation. But in untyped lambda calculus, you don't have a type annotation, so this is going to be just lambda x. And then you make a recursive call. And what about expression E1 applied to E2? You apply this eraser function recursively. What about this type abstraction? And this type abstraction is not found in untyped lambda calculus. This is purely the construct that is dedicated to type. So we erase this type abstraction. So it's going to be just erase E. And finally, this type application. Again, this type application is all about types. So we don't need it. We don't need this part in untyped lambda calculus, so it's going to be erase expression E. We can define eraser function like this one, and then the problem of type reconstruction for system F is take an expression in untyped lambda calculus and then produce a corresponding expression in system F, E prime, which satisfies this equation. So that's the problem of type reconstruction. And this eraser function actually even respects the reduction in system F and untyped lambda calculus. So what that means is that if you have expression E reduced to E prime in system F, now you know that these two types are rare typed. But at runtime, you don't need this information on types, although you can actually take advantage of this type information to optimize your code. but that's beyond the scope of this lecture. So if this is the case, then if you erase expression E, then this one is an expression in untyped lambda calculus. So this is untyped lambda. This one actually reduces to erase of expression E prime. Again, this is also in untyped lambda calculus. And actually, this is not quite correct because it may be that this erase expression E and erase expression E prime might be identical. So for instance, if that is the case, if these two expressions are equal, then still you should be able to show that they are somehow related under reduction. So we have to so we have to use this reflexivity just in case that these two erased expressions are identical. So this erase function actually even respects the reduction in system F, and it correlates this reduction in system F with the reduction in untyped lambda calculus. Let's take a look at an example, which is lambda x dot x. So in untyped lambda, this untyped lambda calculus, and the expression is lambda x applied to x, and we want to add a type, and we obtain a corresponding expression in system F. So what is this expression? Where erase expression E must be, of course, equal to this lambda x dot x. So let's figure out the expression E. So the idea is that first you have to assign a type to this variable x, and then you have this application. So first notice that this expression is not typable in simply typed lambda calculus. In the case of a simply typed lambda calculus, if you assign type A to this variable x, then we have two conflicting requirements. This variable x has a type A, then this variable x must have a type A arrow something, because that's the only way to get the whole expression well typed. Now, the first instance of variable x requires that its type be A arrow something, whereas the second instance of variable x requires that its type should be A, and there's no way to equate these two types. As a result, this is not typable in system F. In simply typed lambda calculus. You cannot convert lambda x dot this expression in a corresponding expression in simply typed lambda calculus. But this is typable actually. This is indeed typable in system F. And the idea is that we'd like to consider this variable x as an identity function. So remember that from the previous lecture, in system F, the type of a given expression might be able to tell you what the expression is doing. So in the case of identity function, perhaps the type is for all alpha, alpha, arrow, alpha. So in fact, if an expression has this type, it must be an identity function. So let's say it has for all alpha, alpha, arrow, alpha. Now, let's say that let's call this type as A. So this type is now called A. So it has type A. So the second instance of variable x has type A. Then first we have to produce type A arrow A from the first instance of variable x. And this is feasible because this variable x has this polymorphic type. All we need is to instantiate this type variable alpha to A. So what we do is to introduce this type application. So this variable x is a type for all alpha, alpha, arrow, alpha. So therefore, this type application has a arrow a. So this is a arrow a, this is a type a. So the whole application is a type a. As a result, this expression, the whole expression, has a type for all alpha, alpha, arrow, arrow, a. But a is actually the same type. So a is this polymorphic type. So it has this type. We can actually expand this one. We can actually expand this one for all alpha, alpha, arrow, alpha, like this one. So this is the result of type reconstruction. Starting with this expression in untitled lambda calculus, we have discovered a corresponding expression in system F, which is this one. And if you erase the type information, you get back this one. If you erase this one and this one, you get back the original expression. So this is an example of a type reconstruction. We successfully managed to convert an expression in untitled lambda calculus to a system F expression. Now, we have now the problem is that not every expression in untitled lambda calculus is typeable. So here's an example. Recall the omega expression, which is lambda x, xx applied to lambda x, xx. This is a valid expression in untitled lambda calculus, but it has no corresponding expression in system F. In other words, this is not typeable. Omega is not typeable. It's not typeable. And the proof is actually quite fascinating. The proof actually exploits a property of system F called normalization. So we are not going to details about this normalization stuff, but the key idea is this normalization property says if you have a well-typed expression in system F, then its reduction eventually terminates. So you may call it termination property. So this is a normalization property, and we can exploit this normalization property to show that it's not actually typeable. So what we have seen so far is the problem is we start with this untyped lambda, and then we'd like to reconstruct the types, type reconstruction, to produce an expression in system F such that we have this equation erase E prime is expression E. So this is E, this is E prime, and we have this connection. So this is a type reconstruction problem. So some expression in untyped lambda calculus is typeable, but there's a counterexample like this omega expression. So not every expression is typeable. Then we have to first decide, given expression E here, we have to decide, is this typeable or not? If this expression is shown to be typeable, then we could try to find the corresponding expression in system F. If it is not typeable, then there's no need to make an attempt. But the real problem here is this question of, is this typeable or not? This problem is actually undecidable. That means that there's no algorithm for this problem. This problem is basically not solvable. So I'm not talking about efficiency in designing and implementing this algorithm for type reconstruction. We are talking about decidability and undecidability, and this problem is undecidable. There's no such algorithm, just like Horting problem. So this is not decidable. And the reason for this undecidability is the system F is too powerful. It's too expressive, too powerful, too expressive. So we can imagine that there is some kind of this spectrum. System F lies at the one extreme, the right extreme, the right end of this spectrum is too powerful, is too expressive, too powerful, and the price that we have to pay for its expressive power is it's not decidable, undecidable. The type reconstruction is undecidable. The plan now is, because system F is not quite a practical language, its type reconstruction is undecidable, so we cannot even it's not actually a good idea to base your practical programming language upon system F. So the plan now is we'd like to reduce its expressive power until we find a language that is less expressive. It's less expressive. Maybe it's a sub-language of system F with some restriction on the way that we use the types. It's less expressive, yet it is decidable. The type reconstruction is decidable. So the quest for now is we'd like to identify such a language that is less expressive than system F. Perhaps it's a sub-language of system F, but its type reconstruction decidable. So this is the topic for the next few lectures.